Hello! Hello everybody. This is Dr. Willow Ariella coming to you to talk about designing, conducting, analyzing, experimenting, interpreting experiments with more than two groups. So we're talking about Chapter 11 of Smith and Davis. So I wanted to highlight or emphasize some points or aspects in this chapter. So the first subject they address in this chapter is adding to the basic building block of the experimental design. So sometimes, as I mentioned, researchers want to move beyond the two-group designs, where you have one independent variable and one dependent variable, so that they can ask more complicated, more interesting questions. And they mentioned that every experimental design is based on a two-group design, the IV and the DV experimental group. The IV and the DV plus where you have a control group. That's the experimental design. And the assumption is that you're using random selection and controlling for extraneous variables. So every experimental design is based on the two-group design. And your questions could be more complicated or sophisticated, but the basic design principles remain constant. So you're building on, no matter how many levels you have of the independent variable, you're building on the basic two-group experimental design. So they go into the multiple group design, and they say that the researcher will need to ask how many independent variables or what levels of independent variables does someone want to have in the experiment. So that's the first question that one might ask oneself. How many independent variables will I use in my experiment? And they have a helpful table or figure, they're calling it, where they show, depending on how many groups or levels the independent variable has, will depend on the statistical analysis that is used, as well as different aspects of the participant groups. And so that's a very helpful figure in 11-1. And so they're, in this chapter we're going to discuss having multiple levels or groups of independent variable. They mentioned that although the one independent variable experiments may be simpler than experiments that use multiple independent variables, they are not inferior in any way. Many students who are designing their first research study decide to throw in everything except the kitchen sink as an independent variable. A well-designed experiment with one independent variable is vastly preferable to a sloppy experiment with many variables thrown together. Remember the principle of parsimony. That is, if one independent variable experiment can answer your questions, use it and don't complicate things needlessly. So this is true whether you're conducting your own study or you're evaluating someone else's. Did it seem like they had the appropriate level of independent variables for their research, given their hypothesis and their research question? Or did they overextend themselves and sort of make their results meaningless? So how many groups or levels is another question that a researcher asks themselves. And the question marks the difference between the multiple group design and the two-group design. As their name implies, a two-group design compares two levels of an independent variable, whereas a multiple group design compares three or more levels of a single independent variable. And so we looked at levels in a previous chapter and assignment. So the differing amounts or types of an independent variable are the levels. They ask a good critical thinking question. On page 233, we learned that the most common type of two-group design uses experimental and control groups. How will the multiple group design differ from that common two-group design? And they mentioned that there are actually two answers to that question. A multiple group design can have a control group. You would just have more than one experimental group. And instead of conducting a two-group experiment to determine whether an independent variable has an effect, a second two-group experiment to determine the optimum amount of your independent variable, you could conduct a multiple group experiment with the control group and the number of treatment groups you want to assess. So again, the treatment groups are the participants in the independent variable who are receiving the independent variable or are randomly assigned to the independent variable. Second, a multiple group design does not have to have a control group if you already know that the independent variable has an effect. But that's a big if. Most of the time, most researchers don't know that. So then they use a study that had 4 experimental groups. And so they use this as their example throughout the chapter. Looking at clothing and how quickly clerks respond to people dressed in different ways. And looking at the information underneath the figure 11.2, the authors discuss support for the experimental hypothesis is not the same as proving the experimental hypothesis. This is a very important and subtle point. So again, you want to look at how does one prove a hypothesis, or is the hypothesis merely supported by the evidence? So support for the experimental hypothesis is not the same as proving the experimental hypothesis. Did the authors of the study prove that the type of role model affects students' buying intentionality? No, they merely demonstrated that there was a difference that was unlikely to have occurred by chance for the role model conditions they use and for their groups of participants. What about using different role models? What about using different research participants, children or older adults, for example? And so we have looked at studies and whether or not their conclusions bear to their data. We've critiqued research to see in media announcements to see if the media announcements match what the research study actually says. So that's kind of, in a way, what they're saying. Do the conclusions that a researcher drew from their results prove a hypothesis or support a hypothesis? And so most of the time authors want to write prove when some of the times that they ought to be writing support. And you have to make critical thinking judgments about that sort of thing. And so they're talking about, can you generalize the results from this particular study to other scenarios and say that the hypothesis is proved? And that's where repeated testing comes into play. Repeated testing helps you get closer to proving a hypothesis, whereas one single study doesn't prove much. It only can tell us a little bit of information. So one study alone, generally speaking, does not prove much. It may suggest something and it may support something, but it doesn't usually prove, unless you've got a very large study and lots of participants and using multiple group design with a placebo group, which medical testing is supposed to do. But we're talking in this class mostly about psychological and social science studies, and unfortunately they often, I don't know if it's often, but too often they don't use, researchers and social scientists don't use a control group. And partly that's because of the kind of research that's done where a control group isn't applicable, like post hoc analysis. And then they ask a good critical thinking question: could you use a multiple group design in such a case where you wanted to test more than 3 conditions? Why or why not? Yes, you could use a multiple group design if you had 4 or 5 role models to assess. In fact, it could be used if there are 10 or 20 role models. So practically speaking, it is rare that multiple group designs are used with more than 4 or 5 groups. But you could. And then they talk about assigning participants and the different procedures that can be used. And again, the note that random assignment serves as an important control procedure to try to eliminate extraneous and compounding variables. Random assignment results in participants who have no relation to participants in other groups. In other words, the groups are independent of each other. And this terminology of independent and between groups and within groups is important. So we'll want to note that for later. But then they talk about using correlated samples instead of independent samples or random assignments. So correlated samples. We know that random assignment should create equal groups, but also that is most likely to work in the long run, or in other words, when we have many participants. If we have few participants, or if we expect only small differences because of the independent variable, we may want more control than random assignment helps. So sometimes we might use non-random methods like correlated samples of assigning participants and end up with correlated groups. And so there are three main ways of creating correlated groups that they discuss, so you can check those out. Although you can see the pros and cons of not using random assignment and using correlated groups. And then on 238, they discuss using a correlated groups design by Walker et al. They say that the authors of this book say, by having people participate in all levels of the independent variable, Walker et al. Did not have to worry about the assumption that the groups were equivalent before the experiment began. By using each person as his or her own control across the 9 measurements, the question of group equality was answered. And so my question to you is, how was it answered? So that's something for you to think about. And then they go into comparing the multiple group and 2-group designs. And so they say, as a matter of fact, all you have to do in order to create a multiple group design is to change a 2-group design into a multiple group design, is add another level or more to your independent variable. So instead of having 4 levels of clothing, you can add 10 or whatever. In Chapter 10, we provided you with an ideal situation for a 2-group design, an experiment in which we merely wish to determine whether our independent variable has an effect. Quite often, such an experiment is not necessarily because that information already exists in the literature. So here they're talking about conducting a good literature review. You should never conduct an experiment to determine whether a particular independent variable has an effect without first conducting a thorough literature search. A very, very important point. If you find no answer in a search, then you should consider conducting a 2-group study. So if you do a thorough literature review, and you know the answer to how thorough is a thorough literature review is not an easy one. And people have different definitions of that. Mostly it's determined by time, but a thorough literature review mostly means that you look through most or all of the relevant journals and maybe go outside the relevancy a little bit, expand your search a little bit outside the most relevant journals and textbooks for the research variables that you're interested in, to see what others have said about it or have said about similar kinds of research. A literature review, a thorough literature review takes a lot of time, and there's no two ways about it, but they're making an important point here about when one should use a 2-group design or go further in their design, and often that's based on the literature review. Not always, but often. And then when you, how do you decide if a two-group or a multiple-group design is appropriate? Although this answer may sound odd, you should think about your future results. What will they look like? What will they mean? Most critically, what will the addition of any groups beyond the basic two tell you? If the information that you expect to find by adding a group or groups is important and meaningful, then by all means add the groups. If, however, you're not really certain what you might learn by adding the two groups, then you may be merely complicating your experiment needlessly. So, working with an experienced researcher, if you're doing a research project, you want to work with somebody who has experience so they can help you, go through these different scenarios and see which ones would be most applicable and relevant to your study. And so in this book, in Smith and Davis, they discuss throughout the book experiments that students conducted with their advisors, and that can mean a mentor or a faculty thesis chair or different things like that. And so if you do a research report as a student, it's often the case, if not always, but I don't know about always, but it's often the case that students work with and consult with and have a faculty member who is experienced in research guiding them and helping them make these kinds of decisions. So they discussed that the Walker experiment had 9 different distances, and they clearly benefited by using a multiple group design. And then they ask a critical thinking question. Suppose Walker et al. Wanted to use a smaller, larger multiple group design. Would it be possible to use such a smaller, large multiple group design? And so it's possible to do a lot of things, but some of the considerations are, is it practical? Can you obtain enough participants, or can they be counted on, or would it be too cumbersome for them to be involved in repeated measures and that sort of thing? So things that we've discussed before you still would consider in your multiple group design. Comparing multiple group designs, so choosing a multiple group design, again, your first consideration in choosing an experimental design should always be your research question. Always. Everything relates to the research question. And then they discussed control issues, so you want to read that section thoroughly. They discussed practical considerations. I want to read that thoroughly. Under variations on the multiple group design, so they mention if we already know that a particular independent variable has an effect, then we can use a multiple group design to help us define the limits of that effect. In this type of experiment, we often add an important control in order to account for a possible placebo effect. So we've discussed placebo a little bit. Helpful to know what that concept is, and also to do research and figure out what a nocebo group is. And then dealing with measured independent variables. So they discuss an ex post facto research. Remember that we cannot randomly assign participants to groups in such research because they already belong to specific groups. So in post hoc research, you're doing something where the participants are being chosen for their groupness. They're already in a particular group, or they've already experienced something. So you're doing research based on something where the independent variable has been set up after the fact, and you didn't really, manipulate the independent variable. You're really just choosing the independent variable. So, so we cannot randomly assign to groups in such research because they already belong to specific groups. Thus, the groups may be different at the beginning of the research, and we cannot draw cause and effect relationships from such experiments because we do not directly control and manipulate the independent variable ourselves. But of course, if done well, ex post facto research can tell us something. All right, so then they go into statistical analysis and going into pretty good breakdowns of some of the statistical procedures that you may know about or will learn about very soon. So they say, we remind you from the previous chapter that experimental design and statistical analysis are intimately linked, as is just about everything in research. You must go through the decision-making process we have outlined before you begin your experiment in order to avoid the possibility that you will run or do your experiment and collect your data only to find out there is no statistical test that you can use to analyze your data. That would be a big bummer. So again, you want to think about all these factors ahead of time, and having someone to bounce off ideas as well as a thorough literature review can help you with this. And so they go into detail about using the analysis of variance, or ANOVA, statistical procedure. So ANOVA is used to analyze designs that include more than one independent variable. So there are different types of ANOVAs, and we need some way to distinguish among them. So in this chapter, we're looking at an ANOVA for one independent variable, which is typically referred to as a one-way ANOVA. You remember that we have considered both multiple and independent groups and multiple correlated groups designs in this chapter. We need two different types of one-way ANOVA to analyze these two types of designs, just as we needed different t-tests in Chapter 10. So it might be helpful to review Chapter 10. So as you can see from Figure 11, when we assign our participants to multiple groups randomly, we will analyze our data with a one-way ANOVA for independent groups. If we use matched sets, natural sets, or repeated measures, we use a one-way ANOVA for correlated groups. So important to know that. So again, under planning your experiment, they talk about the operational definition. They say that is defining the independent, dependent, and external variables in terms of the operations needed to produce them. Also, just about every concept in a research study must be operationally defined. So the participants must be operationally defined. In other words, age range, sex, class, whatever is appropriate to know, or that you want to have included in your study. Even the participants must be operationally defined. So just about every concept in a research study is operationally defined. So then they go into the rationale of ANOVA. So they have a pretty good detail here about understanding between groups variability, error variability, or within groups variability. And so you want to read that section carefully. The variability between the groups response times represents the variability caused by the independent variable. So you want to review that and make sure you understand that, or ask if you have questions. On the other hand, error variability should occur among the participants within each group. Thus its name, within groups variability. And so they're relating this discussion to the table 11.2. One major source of within groups variability is the difference within all the participants in a group, what we have labeled individual differences. Different people will score differently on the dependent variable simply because they are different. And then they go into understanding the between groups variability, the error variability, the variability due to the independent variable, and those sorts of things. So they're breaking down understanding ANOVA, which is very, very helpful. At least I thought it was. So they discuss if our independent variable has a strong treatment effect and creates much more variability than all the error variability, we should find that the numerator of this equation, just above and on that page, is considerably larger than the denominator. So they're saying look at figure 11-4a. So they're giving you a numerator and denominator, and they're also showing it in a pie graph. This result then would be a large F ratio, and they discuss what the F symbol means. If, on the other hand, the independent variable has absolutely no effect, there would be no variability due to the independent variable. Take a look at the F equals variability due to independent variable. Meaning we would add 0 for that factor in the equation. In such a case, our F ratio should be close to 1 because the error variability between groups should approximately equal the error variability within groups. And that is depicted in 11-4b. A simple way to think of ANOVA is to realize that you are dividing the treatment effect, independent variable, by the error, the variability. When the independent variable has a significant effect on the dependent variable, the F ratio will be large. Hopefully that makes sense to you. It made sense to me reading through it, so hopefully it does to you too. When the independent variable has no effect or only a small effect, the F ratio will be small, near 1. So if you're unclear about that, reread it and ask if you have questions. So then they discuss making sense of your statistics or interpretation. So they go through a table of computer statistics that they have as an example. As you will see, adding a third group or more creates an interesting statistical problem. We may have to compute an extra statistical test to explore significant findings. So interpreting computer statistical outputs. They have a table 11.3 where they discuss all the results in that table, which I thought was very helpful and clear. So they mention, as usual, we first look for information about descriptive statistics. If you don't remember what descriptive statistics are, please review that definition. Remember that we recommend that you make sure you have entered your data correctly by checking the means using a calculator. Calculating your means is pretty easy, so it's a good idea that they're proposing. And you can do that for results that anybody else creates in a study. You should be able to calculate the means yourself to see if they made any mistakes. Then they discuss the means. So we do see numerical differences among the means, but we do not know whether the differences are large enough to be significant until we examine the inferential statistics. Again, if you don't remember what the inferential statistics concept means, review that. And then they discuss, we also see the standard deviation and standard error for each group. The times for group 2 are more variable than those for the other 2 groups. So you want to look at the table and see what they're talking about, as well as 95% confidence intervals. The confidence intervals provide a range of scores between which the true population mean should fall. Thus, we are 95% confident that the interval ratio of 40.34 to 57.41 seconds contains the population mean for all clerks responding to customers in casual clothing. So you want to review what they're saying and compare it to the table and see if that makes sense to you. And then they discuss reading the one-way ANOVA response time and what a source table means. The two terms between groups and within groups refer to what? This is really important to understand because this helps with understanding the statistical output information. So between groups is synonymous with our treatment effect, independent variable, and within groups is our error variance. So what's happening within the groups with the participants themselves in that one group? Where is the error because the participants are just different? And so they discuss the sum of squares. And then near the bottom, only 3 groups can contribute to the between groups variability, but many different participants can contribute to within groups variability. Thus, to put them on an equal footing, we have to transform our sums of squares to mean squares. So again, you want to review that and be sure you understand that. Because we have 3 groups, our between groups degrees of freedom are 2, number of groups minus 1. Because we have 24 participants, our within group degrees of freedom are 21. So they explain how they obtain the degrees of freedom in that printout, or the table 11.3. We should note at this point that a mean square is analogous to an estimate of the variance, which you may remember from statistics as the square of the standard deviation. So why is that important? You want to review that section. Then they talk about the F ratio of 4.71. This result means that the variability between our groups is almost 5 times larger than the variability within the groups. Or, perhaps more clearly, the variability caused by the independent variable is almost 5 times larger than the variability resulting from error. And so they have a pie chart on figure 11.5. Finally, we come to the conclusion. Did the different clothing styles have a significant effect? Next to the F ratio in table 11.3, you see prob entry 0.02. This probability of chance of these data, if the null hypothesis is true, we discussed null hypothesis in a previous chapter, is certainly lower than 0.05, so we did find a significant difference. This means that the difference in the response times among the 3 groups of sales clerks probably did not occur by chance. They say you should know how to use a printed F table just in case your computer program does not calculate probabilities. And so they have an F table in the appendix. Thus, if you were using a table rather than the computer output, you would have written P is less than 0.05 or 0.01 less than P less than 0.05 to be as specific as possible. Good point. Alright, then they go into post hoc comparisons, also known as follow-up tests. Post hoc comparisons are statistical comparisons made between group means after finding a significant ratio. Many different post hoc tests exist, and there is much debate over these tests, but that is beyond the scope of this text, so you would learn more about that, for example, in a statistical class. Simply remember that you have to conduct post hoc tests if you find an overall significance in a one-way ANOVA. So in table 11.3, they used a Tukey HSD. Abbreviation means honestly significant difference. Sometimes these things are kind of funny. So Tukey HSD allows you to test all pairwise comparisons, meaning that you can test the difference between all sets of 2 means. And so they discuss how group 2 is significantly different from group 1 and 3 based on the Tukey test. And why did they choose the Tukey test? I don't know. You want to look at other post hoc tests in statistics class to see if there's a better test for whatever reason. As in the previous chapter, we hope that you are learning general principles about computer printouts rather than specific words or terms for which you will blindly search. If you understand the general principles, interchanging between groups with clothing or the name of some other IV should not be problematical for you, because different statistical programs may have different ways of getting at the same thing. For example, don't be surprised to see the label error rather than within groups. Both terms mean the same thing. The important conclusion is that given the same data, any 2 programs should find the same results. And given your understanding of general principles and what these different kinds of errors and between groups, within groups, and that sort of thing mean, then hopefully you'll understand other people's research results and their statistics. And then they discuss translating statistics into words. Let us remind you, as we did in Chapter 10, that the results of any statistical test are only as good as your experimental procedures. So again, if you have sloppy data, sloppy experiment, sloppy study, your statistical analyses are sloppy, that means that they won't be helpful or meaningful. And also, one of the objectives of this class is for students to learn how to determine whether or not a research study was done well or done sloppily. So hopefully you'll be able to catch sloppy research after this class. And then they ask an important critical thinking question on 252. Although this conclusion is technically correct, they wrote that above the blue box, it is a poor conclusion. Why? And how would you revise this conclusion to make it better? And this is a really important point. This conclusion is poor because it is incomplete. Reread the sentence and decide what you can learn from it. So you can stop this, reread the sentence above the blue box, and then think about it if you'd like. And then they say, all you know is that students who wore some type of clothing were weighted on more quickly than other students who wore some other clothing. Thus you know that clothes can make a difference, but you don't know which type of clothing led to faster responses. To write a good conclusion, we must go back to our inferential statistics, particularly the post hoc tests. And then they discuss more information about the statistics, and then they say, no other mean differences were significant. We must determine how to communicate our statistical findings in APA format. So anyway, the important point that they're making about how researchers write about their results is very important. So they wrote, under translating statistics into words, based on our inferential statistics, we conclude that the clothing customers wear is important because clerks took differing amounts of time to wait on customers depending on how they were dressed. But Smith and Davis said this conclusion is poor because it is incomplete. So you want to reread that conclusion and think about what Smith and Davis is saying about how to write a complete and an appropriate conclusion. You don't want to draw inferences or say some kind of result that isn't accurate or valid based on your study or your statistical information. Very important point. And then underneath this conclusion is poor, they say, we must determine how to communicate our statistical findings in APA format. And so this is very important. I want to emphasize, I think I've said it in another video, but statistics, numbers, tables, graphs, pie charts, none of that stands alone. In a research study, researchers, the authors of the study, must clearly report in words their numerical findings, ostensibly so that anybody reading the research could figure out what the numbers mean and that they're accurately conveyed. And so you've got to report the numbers in words. The words alone should convey the meaning of our results. Could someone with no statistical background read and understand these sentences if we remove the numbers? We think so. So that's one of the goals of writing out in words your statistics. The reader has an expectation about what information will be given because we write our results in the standard APA format. And so they provide good examples of how to rewrite the statistics into words. Page 254, they talk about this situation illustrates one of our pet peeves with computerized statistical programs. When you studied distributions in your stats class, what did you learn about the tails of those distributions? Reread tails if you're not sure what that means in the previous chapter. We hope you learned that the tails of distributions are asymptotic. That is, the tails extend into infinity and never touch the baseline. So that means that the probability of statistics is never 0.000. But they say that some programs, computer statistics software, have a limited number of columns to work with, or they don't think about this issue, so they have the computer print a probability of 0.000, implying there is no uncertainty about this result. In light of this problem, we advise you to list P is less than 0.001 if you ever find such a result on your computer printout. So they're just making a point that it's never, in research, it is never, someone is never able to prove that their results are absolutely, positively, no room for error. Anyway, well, that was an important point. So they ask an important critical thinking question On page 256, there are 5 important differences between this conclusion and the conclusion drawn for the independent groups in NOVA. Can you find them? So I encourage you to read through that. And then the continuing research problem. Is our research project complete at this point? As you might have realized, we could compare an endless number of styles of dress. So they discussed, that one can extend or replicate a research study to just about infinity. So a research question is almost never definitively answered because there can often be infinite ways to examine the independent variable, or different measures to use for the dependent variable, or different participants to utilize in a group to see if we can expand the generalizability. So really important question. So I hope this was helpful for you. Thanks for your time and attention, and look forward to your comments and thoughts in class. Aloha.